Okay, now we're going to take a look at an example where the limit comparison test will be used to determine that a series converges. So let's look at this example right here. We have the series sum k equals 1 to infinity of cube root of the quantity k squared plus 1 divided by the cube root of quantity k to the 6th plus 2. Okay, so let's go ahead and look at this. And the first thing we're going to do is we're going to look at what is the dominant term of the numerator. So the numerator is going to behave like, well, the dominant bit of this numerator is this cube root of k squared. Okay, and that's, I think things with these radical signs are kind of ugly. So we're going to write this as k squared, and then we're going to take that to the 1/3, so that's k to the 2/3. Okay, and the denominator, that thing is going to behave like the cube root of k to the 6th plus 2. So the key feature of that is going to be this k to the 6th that we take a cube root of. So that's just going to give us k squared. So the whole expression is going to be roughly like k to the 2/3 over k squared. So, right, that's going to give us, we're going to put the squared back as a 2/3. Okay, so that's going to give us k to the 2/3 minus 6/3. So that's k to the minus 4/3. And now that's going to give us then a p series for p equals 4/3. Which is bigger than 1. So the series k equals 1 to infinity of 1 over k to the 4/3 converges. So now the thing we need to do is, right, we know what the behavior of our series is. Our series is behaving like this k to the negative 4/3 that we just looked at. Now what we need to do is to use the limit comparison test to make that precise. So that's what we're going to do next. Okay, so what we need to do is we need to look at the limit now as k goes to infinity of the term of our series divided by the p series that we're looking at. Right, so this is going to be 1 over k to the 4/3. That's the one we're comparing it to. And then up here we had the cube root of k squared plus 1, and then here we had the cube root of k to the 6th plus 2. Okay, so that's the limit as k goes to infinity. Right, that part doesn't change. This k, dividing by 1 over k to the 4/3 is the same as multiplying everything by k to the 4/3. So here we have k to the 4/3. And then here, I'm going to replace our radical by a fractional exponent. And downstairs, we have k to the 6th plus 2. And so this is limit as k goes to infinity. And now, if you notice, we have this 1/3 exponent we can factor out everywhere. So that's going to be k to the 4th times k squared plus 1, and then downstairs we have k to the 6th plus 2. So this is now limit as k goes to infinity. I'm going to move that exponent to the 1/3 out, and we then get k to the 6th plus k to the 4th divided by k to the 6th plus 2. And now the limit of this as k goes to infinity is indeed driven by the ratio of the top powers here. So this is going to give us 1 to the 1/3 power, which is 1. And that's a constant, right? That's a constant that's non-zero and finite. So by the limit comparison test, that gives that our series converges. Right? Because we saw that this test series, this 1 over k to the 4/3, was a p-series that converged. So there we've seen an example where we used the limit comparison test in order to see that the series converges. Okay, in our next video, we're going to see a little bit of a more delicate use case of this limit comparison test.